geometry course. Today we're going to be talking about an exciting and strange topic called the Euler line. And this monstrosity of a figure is supposed to represent the Euler line. Actually, the purpose of this figure is to review some of the ideas of the center of the triangle here. So this crazy triangle is supposed to represent all four triangle centers here. So I've chosen the color names in supposed to be a cute way so that you can associate them with their meanings. So the mint color is for midpoints and median. The cerulean color, which is the light blue, is the circumcenter. The orange color is the orthocenter, and the indigo color is the incenter. So that's supposed to be a cute way of keeping track of what's going on here. Let's hide some of this stuff so that we can actually dig in and see some of it, focus our attention on some of it. So I'm going to hide two out of these constructions and then focus on the others. So here in orange, we can see it's the construction of the orthocenter in the usual way. We drop three altitudes, we find the point of intersection, easy peasy. In green, we see, or mint, I should say, in mint, we see the entire construction of the medians, that is AJ, BK, CL, those are medians, the medial triangle, JKL, and the intersection point of the medians, which is called the centroid here, which is labeled G. Okay, so what else do we have here? We also have the construction of the circumcircle. So this circumcircle and the circumcenter are constructed by finding the point of intersection of the perpendicular bisectors of the three edges of the triangle. So the perpendicular bisector of BC is this vertical blue line. The perpendicular bisector of AC is this blue line. And the perpendicular bisector of AB is this blue line here. They intersect here at the circumcenter O, which is the center of the circumcircle. And then finally, we have the angle bisectors. So we have three angle bisectors here at A, at B, and at C, and they intersect at the incenter of this triangle. Now, what I'm going to do here is I'm going to move the triangle around, and hopefully you'll start to see that there seems to be some sort of relationship between the centers. All four of them seem to lie kind of along a straight line here. But if you look closely, one of them is not like the others. One of them does not lie on the straight line that contains the others. So in this configuration, for example, you can see the circumcenter is here, the centroid is here, the orthocenter is here. They do appear to lie on a straight line, but the incenter is not on that line. And you can see the same thing kind of here. I've placed the orthocenter here, the centroid, and the circumcenter. They seem to lie on a line, but the incenter is not on that line. So that's going to be a general expectation. The orthocenter, the centroid, and the circumcenter do lie on a line together, but the incenter does not lie on that line. So for that reason, I'm going to remove the incenter entirely from this picture, and we won't talk about it for the rest of the video. So now we have the three centers that remain, the circumcenter, the centroid, and the orthocenter of the triangle. Everything related to the circumcenter is in light blue. Everything related to the median, the medial triangle, and the centroid is in this mint color, and everything related to the orthocenter is in orange. Now, we wish to show that the orthocenter, the centroid, and the circumcenter all lie on a line together. So what do we need to do in order to show that? What I'm going to do first is I'm going to produce two straight lines. I'm going to connect O to G using a straight line and G to H using a straight line. Now, immediately we see the line, which is the Euler line. But for the purposes of the proof, I do not wish to assume that this line is a straight line. So for example, I don't want to argue about the vertical angles by the meeting of two straight lines, because I don't want to accidentally assume that OGH is actually a straight line. Angle OGH might be 179 degrees, for example, and I want to entertain that possibility so that I don't accidentally assume what I'm trying to prove here. So what I'm trying to prove is that O, G, and H are collinear. Actually, we're going to prove slightly more than this in this video. So the first thing I want to do is I want to focus your attention on these two red triangles here. Triangle JOG and triangle AHG. Now, clearly, they're not congruent. Of course, one is a lot bigger than the other, but they look like they might be similar. And even as I adjust the triangle, these two even as I adjust the shape of ABC, these two red triangles appear to remain similar. And so there's a chance, there seems to be some hope of proving that they are similar. Now, you might think maybe it's easy to prove that they're similar. Maybe it's just a matter of recognizing that this angle equals that one, which is actually pretty easy, and recognizing that these two angles are equal because they're vertical angles across a straight line. Well, if only. If only this were known to be a straight line, but that's what we're trying to prove, and so we can't take that route. So instead, we're going to use a different strategy to prove that these two triangles are similar. We're going to use the side angle side similarity criterion here. I'm going to work out something about this side in relation to that one. I'm going to work out something about this side in relation to that one. And I'm going to work out something about this sharper angle in relation to that sharper angle here. Now, before I will have the opportunity to reason about the relationship between this side and that one, I need to focus our attention on two other triangles, which are now shaded in gray. So these triangles here, which connect J and K to O and A and B to H, these triangles are going to be important in figuring out how this length here relates to that length there. So let's now focus our attention on triangles ABH and JKO in the hopes, obviously they're not congruent, in the hopes of proving that they are similar. This is actually an easy one, relatively speaking. JK is already known to be parallel to AB. We proved that when we analyzed the medial triangle, and noticed that JKL is the medial triangle here. We proved that the segments of the medial triangle are parallel to the segments of the original triangle. So JK is parallel to AB. Moreover, JO is parallel to AH. Now I could say that's because they're both vertical, but that's not really the point here. The point is they're both perpendicular to BC. JO was constructed as the perpendicular bisector of the segment BC, and AH was constructed as the altitude, which is also perpendicular to BC. So both AH and JO are known perpendicular to BC, so they're parallel to each other. So this line here is parallel to this line here. What about these guys? What about this one here and this one there? Well, for these, it's the same deal. KO is constructed as the perpendicular bisector of AC. And BH is one of the altitudes of this triangle perpendicular to AC. So again, BH and KO are both known perpendicular to the segment AC, and therefore they're parallel to each other. So if these sides are all parallel to these sides, correspondingly, then these angles must be equal. This angle at K must be this angle at B. This angle at J must be this angle at A. This angle at H must be this angle at O. Okay, so that gives us the similarity. Do we also know the ratio of the sides, right? We know then that AB over JK is equal to BH over KO, which is equal to AH over JO. But do we know that common ratio that all of those pairs of sides exhibit? Yes, we do. When we analyzed the medial triangle, we realized that this length JK, the length along the medial triangle, is exactly half of the corresponding length on the original triangle. And so we know that JK is exactly half of AB. And that means that all the other pairs are exactly 2-to-1 ratios. BH is exactly double KO, and JO is exactly half of AH. So notice that's the conclusion that we actually want here from the gray triangles. The gray triangles have allowed us to make a conclusion that's relevant to the red triangles, namely that JO is exactly half of AH. So that's the conclusion that we wanted here. The write-up there will be a link in the video description with the write-up of this in case you're having trouble writing it all down. So we've established now that JO is half of AH. Now let's look at the length AG and the length JG. Now these triangles look isosceles, and so we might say that, oh, AG and AH are equal, but that's just a coincidence of the way I've arranged it here. These triangles certainly don't have to be isosceles that way. So let's not make any incorrect assumptions here. what is the relationship between AG and JG? Well, this has to do with something that we proved when we were reasoning about the centroid. Quite a while ago, we reasoned about the centroid and its relationship to the medians, and we realized that the centroid trisects the medians. That is, the centroid cuts the medians of the triangle into parts. It's not the midpoint of them, it cuts them into 1/3 and 2/3 size segments. So in other words, this length BG is exactly 2/3 of the entire centroid BK, and this length KG is exactly 1/3 of the same. Well, this AJ is a median of this triangle, and G is the centroid of the triangle, and so G lies exactly 2/3 of the way along it. If that's the case, then GJ must be 1/3 of that median, and GA must be 2/3 of that median, which means that JG is exactly half of AG. So we're making some headway into these red triangles here. We've got JO is exactly half of AH, and we've got JG is exactly half of AG. Now, we've got two sides in proportion to one another. If we want the triangles similar, we can either reason about the third side, or we can reason about the angle between those two sides. That's the easier method here, so let's do that. This angle at A is an angle made by this line. Now, this line AJ is a straight line. We know that that is a centroid, we know that that is a median of the original triangle. This angle at A is made by that line, which is this median, as it meets this line AH, which is an altitude. We have already argued that AH is parallel to JO. And so what we have here is two parallel lines, JO in blue, AH in orange, cut by a transversal AJ. And we know that angles created by a transversal across two parallel lines will be equal here. These are called alternate interior angles of the transversal cutting the two parallel lines. So this red angle at J, which is technically OJG, and this red angle at A, which is technically HAG, are alternate interior angles of two parallel lines cut by a transversal, so they're equal. So this angle at J and this angle at A are equal. So we have, to sum up, we have JO is half of AH, we have JG is half of AG, and we have this angle at A is equal to this angle at A. So that's all we need for similarity. We'll apply side angle side similarity to these two red triangles. What do we get from that? What does it give us? Well, it gives us that the triangles are similar. Well, who cares they're similar? Well, the secret here is, now that we know they're similar, then this angle formed at G must equal this angle formed at G, which the only way that can possibly happen, given that AJ is a straight line, the only way that this line segment here, OG, can form the same angle with that straight line as this line segment here, GH, can form on this side. The only way those two angles can be equal is if OGH is a straight line after all. So we conclude that OGH is a straight line after all. And this is the core statement of the Euler Line theorem, that the circumcenter of the triangle, the centroid of the triangle, and the orthocenter of the triangle lie together on a straight line. But more is clearly true here. If we have proven that these triangles are in fact similar, and we've already established that the ratio is a 1-to-2 ratio, then we can say much more about the relationship between these centers. We can say in particular that the distance between the centroid and the orthocenter is always exactly double the distance between the centroid and the orthocenter, right? This distance is exactly half of this longer distance. So in other words, for any triangle at all, the circumcenter, the centroid, and the orthocenter will lie on a straight line. The centroid will be between the others, and it won't be the midpoint. It will be 1/3 of the way from the circumcenter to the orthocenter. We always have these three centers in this configuration. And that's pretty convenient to know apparently, if you know two of these centers, it's quite easy to get the third. All you have to do is measure out the ratios correctly, and you'll figure out where the third center is. So that's the statement. That's the proof of the fundamental statement of the Euler line.